Welcome to section 1.6, equilibria and the phase line. So we're going to start this section with the patented Jason Barnett. We've already been doing this. We already have talked about equilibrium. We've already talked about autonomous differential equations. And I claim that we've already talked about phase lines too. So recall something that we already know, right? dy dt equaling f if it's solely a function of the dependent variable, there's no t's in here, just the dependent variable y, right? Then this is autonomous. Autonomous meaning self-governing. It doesn't depend on time. You know, if you get one solution, you get infinitely many more solutions by doing a horizontal shift. And we know what we know what slope fields look like for autonomous differential equations. Here we have an autonomous a slope field for the autonomous differential equation y prime is equal to 1 minus y times y. It's autonomous. There's no t's. And we know that it's autonomous because, right, if you know the slope for one value of y, you know the slope for all of those t's. And a different value, if you know it for one t, you know it for all t's at that y, and so on. So my claim to you is that, well, this is rather redundant. Why don't we just look for one value of t, right? If you know it for one, if you know this red thing, you know the whole slope field, right? Well, that's basically what the phase line is. The phase line is saying, okay, let's take this two-dimensional graph and say it's one-dimensional. And what we do is, let me translate this over a little bit. Oops. Oh, it doesn't matter that the red thing didn't move because it's autonomous. All according to plan here, everyone. Let's move some more. All right. And now what we're going to do, actually, hold on, a little less. What we're going to do is we're going to look at the number line in the vertical direction. And we're going to plot the equilibrium. The equilibrium is at y equals 0, and there's another one at y equals 1. Right? Equilibrium is what values of y make the derivative 0, and then we're just going to stay there forever. And now, what I'm going to do is I'm just going to plot the direction of the slope. Is the slope going down here or up here? This is negative slope. The function's going down. So what I'm going to do is draw a down arrow. And the slope's still negative, it's still negative, it's changing, but we're not going to include that information in our phase line. And then it's kind of hard to see here. I could zoom in, but everything over here has a positive slope. Positive slope means things are increasing, we're going up. In this interval, we're always going down. In this interval, we're always going up. And over here, the slope is always going down. So we're going to write an arrow saying that we're going down because the slope is negative. The function's going down. And there you have it. That's your first phase line. Your first phase line, it's just showing the slope field of the autonomous differential equation and simplifying it, okay, on a number line. So usually what we would do to actually draw it, right, is we'd plot the equilibrium. This is y equals 1. This is y equals 0. If we're above 1, we're decreasing to 1. If we're between 0 and 1, we're increasing to 1. If we're below 0, we're decreasing down. This is what a phase line looks like. And again, we do lose information, right? Because this doesn't separate between a small decreasing slope and a big decreasing slope. This doesn't distinguish the two things. But this is what phase lines are. This is a nice intro video. I don't expect you to know everything about phase lines. We'll talk a lot more about what these are, how to work with them, how to create them, how to read them, and what you can do with them in the future videos. But this is the introduction. Here it is.